Okay, let's do some fixed point math. In 244, you went over fixed point math using assembly language, and we can do the same in C. It's a little easier in C. We don't have to, work at it in such detail. And we can use the same data types that we've already created. It's just a matter of how we're interpreting the data. So first, let's look at an example we'll work on. And this example, we're going to output data to the DAC. So we have our DAC. And the output, we'll call it Vout. The input, I'll just call it DAT. We know the register name is longer than that, but we'll start with that. A little easier to write out. Okay, so we'll have some kind of task or ISR writing data to the DAT register of the DAC. And so that is grabbing data from our lookup table, say. The sources and everything could be anything. It's just this example as a lookup table. And that has a bunch of samples that create a function. And so that function I'll call f, and I'll also call f lookup, and we'll see the difference between those two in a little bit. Well, we're also going to grab an input from the ADC. And this is going to be a volume control or amplitude control for the data, the function data going out to the DAC. And we'll call this, well, first of all, it's the ADC. And I'll just say ADCR for the result register. And then we'll also call this V for volume. Okay, so this is a really typical example of what we would do in some embedded system where we have sensors and variables and data that we have to combine in order to send something out in a certain form. All right, so we always want to start on the output. What do we want Vout to be? Okay, and Vout is, we're on the output of the DAC is 0 to 3.3 volts, right? And so we want some function that's setting on a DC value around 165. And let's say it's a sine wave. So it looks like this, right? That's what we're aiming for on this output. Well, the equation for this, Vout, would be Vref, and here we have, remember, we could configure Vref for the DAC. Here we're going to be assuming Vref is set to 3.3, but it doesn't matter. Vref over 2 times V times F. All right, so V is the function that we're grabbing samples from the lookup table. V is the volume control from the ADC. And then Vref over 2 is a scaling factor. Notice the volume here is only in this term, not in this term. In the last lab, you combined this DC offset with the AC value in the lookup table, most likely. Maybe some of you didn't. But most likely you combined the DC offset and the function in the lookup table. So if we were to just multiply V by that number, not only does the function amplitude change, but this DC offset changes. And we don't want that to change. We want the function to get smaller, but still sitting on the same DC offset. So this volume, it's important to apply it to just this term. All right, the volume is going to range from 0 to 1 in this equation, and the function is going to range from -1 to 1, right? Say like a sine wave or something like that, right? And so if this is the case, then we know that the range of this equation is Vref over 2 plus Vref over 2, so that's Vref, or full scale, to Vref minus Vref over 2 minus Vref over 2, which is 0, and that's this value here. Okay? So this is just regular math. It's straightforward, nothing new, but this isn't all there is to it. Let's go back and figure out what we need to do in this task to combine the function and the volume to get our samples that go to the DAT. So the first step we need to make is to go from V out to DAT, and that's the equation that we get from the D to A converter, and that is V out is Vref times 1 plus DAT over 2 to the 12. Okay? So if the value we write here is 0, then the output's 0. If the value we write here is the maximum value of a 12-bit number, we add 1, we end up with 2 to the 12, divided by 2 to the 12, so we get Vref, which is this peak, right? Vref is up here. All right, so we have these two equations for our V out, so now we just need to combine them. The first thing we can do is get rid of the Vrefs. It's in every term. So now we have 1/2 plus 1/2 times V times F is equal to 1 plus DAT over 2 to the 12. Right? So again, what we're trying to do is get to DAT. We need to figure out what DAT needs to be. So we're going to get that alone. And in order to do that, we'll move this 2 to the 12 over here, so we end up with 2 to the 12 divided by 2, that's 2 to the 11. In this constant term, we also have this 1, so we subtract 1, put parentheses around here, plus 2 to the 12 over 2 is 2 to the 11, times V times F is equal to the DAC input. Right? So this is what we want to do. This right here is what we want to do. We want to take our volume and our function, multiply them together, multiply them by 2 to the 11, add that to this. Well, that's not quite right. Because remember, this volume is a number from 0 to 1, and this function is a number between -1 and 1. We know that this volume is coming from the A to D converter. That's a 16-bit value, and it's unsigned 16-bit because it's a single-ended ADC value. And so it goes from 0 to FFFF. So we need to convert this sample, this ADCR, this ADCR, what is this equal to? This is equal to the volume, which is the number from 0 to 1, times what? Well, what we have is a 16-bit unsigned fraction. Okay? Which means that we have 16 fractional bits, and so this V, this result from the ADC is equal to the V, the fraction, times 2 to the 16, right? If we have 16 fractional bits, if we multiply that 2 to the 16 by the numbers 0 through 1, then we end up with the ADC result. And this is the same as taking the ADC result, dividing by 2 to the 16, and we would get this number between 0 and 1. All right. We looked at this in 244, and so I made sure to put the notes in the Canvas site. Okay, so that's the ADC value is the volume value 0 to 1 times 2 to the 16. 16-bit unsigned fraction. And so what type is that? Is that some new data type? No. This is just an int 16u. It's just how we interpret it. The number is exactly the same. It's an int 16u. It's just how we're going to interpret it. Okay. So now the lookup table. This function here is coming from the lookup table. The f lookup are the values coming from the lookup table. And depending on how you do this, these can be 12-bit values or 16-bit values. If you recall, the DAC has 12-bit inputs, so some of you may have created a 12-bit lookup table. Of course, it can't be 12 bits. It has to be 16 bits, but the 16 bits are limited to 12-bit values, right? And then those could be directly passed on to the DAT with the easier, less shifting writes. And that's what I did. I made 12-bit values here so that the write to the DAC is faster, fewer operations. We could certainly do it with 16-bit. We would just have a few extra shifts. And in fact, a few extra shifts may not even increase the number of clock cycles. So it's possible to do it with 16 bits too. But let's just say it's 12 bits. So the lookup table values, 12-bit values, are equal to the function times 2. Now, is it 12 or 11? Well, these are 12-bit signed fractions. Okay? So that means that there are 11 fractional bits and 1 signed bit. If you recall from 244, we have that 1 signed bit, then the radix point and all the rest of the bits. Okay? So that would be 2 to the 11. So this number between -1 and 1, we multiply it by 2 to the 11, and we get the values from the lookup table. So this is with 12-bit samples. If you have 16-bit samples, then our lookup table is just going to be f2 to the 15, right, for 16-bit samples. Process is all the same. It's just a matter of how many times we need to shift left or right. All right. So now we have this equation, but we need to get it in terms of the ADC sample and the lookup table values. So we take 2 to the 11 minus 1, which is equal to 2047, plus 2 to the 11 Okay, V is now this A to D sample divided by 2 to the 16, so that's A, D, CR divided by 2 to the 16 times the function is now equal to the lookup table value divided by 2 to the 11. So that's the function from the lookup table divided by 2 to the 11. And that is equal to the D to A input. All right, so now we can simplify this. We can cancel out this 2 to 11 and this 2 to the 11. So now we just get this divide by 2 to the 16. Now it's always important to remember that when we're dealing with fixed point numbers, that we always do multiplications first and wait for divisions until the very end. And why is that? Well, what if we did something like this? If we took 9 and we wanted to divide it by 10, right? What if we did this in C with fixed point numbers? What would we get? We would get 0. Because the answer is always going to be an integer. And of course, 9 divided by 10, the integer part is 0. So we're just going to get a 0 there. So we always want to do the shifting or the multiplications first in the numerator before we do any division. So that's what we'll do. All right, I decided to go a different route here. And we've got pen, so let's cross that off. All right. Right, so let's take this. We now have 2047 plus A, D, C, R, so the A to D result, times the lookup table value, and then divided by 2 to the 16. Remember what that is. That's simply shifting right 16 times. Okay? So notice the parentheses here. We always want to do this multiplication first before we do this shifting. All right, well, so we're almost there. We have a constant here. We have the value from the A to D converter. We have the value from the lookup table. Multiply those together, and then we shift over 16 times, and then that goes into the D to A input register. The issue now is what happens here. We have basically a 12-bit number. We can say 16, but it's going to be 16, just limited to the magnitudes of a 12-bit, multiplied by a 16-bit number. And so we have to make sure that the result destination is big enough. And if you recall in the assembly class, we had to make sure to create a register space so that when we did this 16-bit times 16-bit, the result ended up into a 32-bit register. We don't have to worry about those details in C. All we have to do is make sure that we have this cast to an int 32s, right? So this is a int 16s. This is int 16u. So if we take an int 16u, multiply it with an int 16s, we know that every result from this will fit in an int 32s. So we end up with a 32-bit number when we multiply these together. And then we shift it over 16 times. So now we have this 32-bit number shifted over 16 times, so we end up with a final value of an int 16s, right? And this is an int 16u here. All right, so we multiply, or we add this to this. We know because of the range that it'll always fit in that 16-bit signed number, or actually the result is unsigned because we have this. This will never be bigger than this, so we end up with an unsigned number for the overall thing. Is an int 16u. All right, and that goes into that. Okay, so I think we all know how to do this in C. You can see that the difference between this and the regular math equation, which was this or this, is that we have these shifts involved. We have to figure out what the data types here, how are we interpreting them? We're interpreting them as a 16-bit unsigned or 16-bit signed fractions. And then that tells us how many decimal points we need to shift over. And we combine the 2 to 11 up here with down here we have 2 to the 27, but then these 2 to 11s cancel, so we end up with 2 to the 16 for the shifts. All right? We certainly wouldn't want to multiply these together and then shift it left 11 times and then shift it right 27 times. In order to be able to shift left 11 times to do this, we would need a result that's larger than 32 bits. And once you get something larger than 32 bits on the ARM core, then you're going to be slowing down the process. All right, so we want to cancel these out, not just blindly shift left 11 times and then shift right 27 times. Okay, so that is how we would do the math. And again, I've assumed that we have 12-bit samples in the lookup table. This would be quite easy if we converted this to 16-bit samples, right? We'd just plug this into here instead of this. We can also write 16-bit samples to the D to A input. If you recall, there's two different ways of doing that. That just adds a shift of 4 when we're writing to the DAT. So either way works. You just have to keep track of the number of shifts, and you'll notice that. I mean, the best thing to do on this this type of thing is to look at the output and turn the potentiometer and see what happens. You know, if you're getting a tiny little sine wave on your offset, you know you probably shifted too many times. If you're saturating the output, you're shifting not enough times or whatever. So it's really good to watch that output on your Logic 8 in the analog mode. All right, that's some math.